of solar water sustainability. How cutting-edge research is capturing water to tackle scarcity. Guihua, the University of Texas at Austin.
On November 9th, 1989, I was a third-grade student and aware of this historical event from international news. The memorable image I could recall from television was that many families were reuniting in Germany.
Thank you. Good morning, everyone. It's my great pleasure and honor to be here to share about our research on the topic of addressing energy-water accessibility. So as we know, water is essential to our life. So using water, our body can function well. So as a universal solvent that help transport oxygen and nutrients throughout our body, so water enables many functions for living organisms. So as this slide shows, so the water contains, our human body contains over 60 to 70% of water, and the water helps us to maintain and regulate our body temperature and digest the food and flushing out all unwanted toxins from our body. So people believe without water, so we cannot survive even for 3 days. Water and energy are at the heart of sustainable development for human society. So clean water and energy are always intertwined to each other. Both are essential for human life. So currently, there are 3 billion people living in the high water stress areas. More importantly, with population growth, economic growth, and climate change, they are driving more and more global demands for clean energy and clean water. So that to the unprecedented levels as population, as this slide shows, by 2040, there's a growing unprecedented level of water shortage. So there's not to mention, there's a worsening situation due to the water pollution and uneven distribution of water resources. So in recent decades, particularly since the pandemic, there's this growing concept of water, energy, food nexus, which attracted significant attention across academic research. So this concept emphasizes the key idea of the production, consumption chain of the water, energy, food are all intricately related to each other. And critically important for the future water, energy, food nexus is to create more sustainable and climate resilient solutions. So this requires transition to renewable energy to make the overall process more sustainable, as well as developing the decentralized solution to make our community more resilient. So water scarcity is a serious global crisis with increased world population, but very limited freshwater resource. We have to tap into this most abundant water source, such as the seawater, which contains over 90% of the Earth's water. So how to turn seawater into usable clean water becomes one of the most promising yet pressing scientific and technological challenges of our time. So hopefully today I'm going to show you these 2 promising solutions that can address this need of creating clean water using only sunlight and air. So there are several industry level of desalination technology, such in this slide shows the membrane to the left is membrane-based, the reverse osmosis process, and the right is the thermal-based desalination. So they critically depend on the natural water source and more feasible in the coast area. And also, it is more suitable for centralized production, often involving the high infrastructure costs and also high energy consumption. For example, a typical seawater RO plant requires about 2 to 3 kilowatt-hour to produce 1 cubic meter of the water. And a thermal desalination plant can use up to 10 times of that amount of water. These critical constraints call for significant technology innovation. So one of the great challenges is how to use renewable energy to produce clean water. And as we know, sunlight is the most abundant and sustainable energy source. So solar-powered water purification is a promising means, sometimes called solar steel or solar vapor generation, to produce clean water from seawater or even wastewater. So critical challenge here is sunlight is diffusive. It cannot meet high demand for efficient water evaporation, and often require very complex solar concentrator to produce enough clean water. So there are 3 key steps in this technology. One is you need to have very high solar absorption. And the second is you want them to concentrate your heat at water and air interface. So this really motivates the conventional bulk heating to avoid the energy loss to the bulk heating, to the interfacial evaporation, to concentrate light, to do the job of evaporating water very efficiently. That also requires sufficient water transport to the evaporation front to maintain the high evaporation rate. So to address these challenges, we turn to the soft matter, particularly hydrogels. As the previous speaker shows, the hydrogel can be very useful in many ways. Traditionally, you can find it in our common life. For example, baby diapers, the contact lenses, and even for many of the biological-related applications. So hydrogel is gel-like structures, and from material level, it is a highly cross-linked network that can contain a significant amount of water and then maintaining these 3D structures. So in 2018, we demonstrated hydrogel, the first hydrogel evaporator that is actually having two key components. One is the solar absorptive PPY, that's the polypyrrole, and the other is hydrophilic PVA, polyvinyl alcohols, with the hierarchical nanostructures. So they can offer very efficient water transport to the evaporation surfaces, but also, most importantly, they can confine this solar absorbed energy to localize, let's heat up these molecular meshes. So we discovered these hydrogel are very unique, and they have this highly tunable solar evaporation behavior. Given this polymer chemistry, you can change polymer-water interaction. So they are really like no other materials. So our first generation of the hydrogel evaporator already yielding these record high solar evaporation rates. So this plot actually shows how we compare with state-of-the-art previously reported in literature. So we are double of what has been reported, over 3 kilograms of the water per square meter of active gel and also per hour. And that's also more than 3 times of the commercial solar steels. So our prototype design, based on our gel evaporator put on top of our engineering building, already yields the potential daily water about 25 liter per square meter of these active gels. That is actually enough clean water for a household of 4. So with this initial discovery, we have greatly expanded these research directions to show hydrogel as a very powerful platform for solar water purification. So this slide highlights several key areas from better understanding the polymer and the solar absorptive particle interaction for energy confinement, and to regulating polymer-water interaction by tuning polymer hydrobility, polymer network, by exploring surface topology, surface wetting effects, and then to design more additive functions such as antibacterial, anti-fouling, and VOC removal functions. But all these efforts as with the goal of producing hydrogen-based solar purification systems for household needs and potentially even for a larger system. So today I'm going to show you another very promising technology is tapping into atmospheric water, which has over 13,000 cubic kilometers of the water. So it is very ubiquitous and it's a sustainable water source. It's present anytime and anywhere. And there are 2 current technology, including fog collections, so they actually will allow the collection, but with very clear geographic and climate conditions limitation. They're highly dependent on relative humidity and temperature, and also doing is a process very energy intensive. So sorption-based moisture harvesting actually can go over this limitation on the geography or hydrological conditions, so to really promote the global needs. So we have been focusing on sorption-based atmospheric water harvesting for the recent years. So 2 fundamental steps in this technology. So the first is moisture sorption. So this typically is through the physical or chemical interaction between water vapor and your sorbent materials. So the most important is actually the second step. As we know, desiccant the lower humidity, they can absorb the water, but you're never producing clean water out of that because high absorption at first step often means the high energy penalty when you want to release water. Usually involves significant heat to go over this evaporation condensation process to get clean water. So we actually demonstrate to the field is there's new functions that you don't need to go over this significant energy barrier. To use thermoresponsive gel, they can directly release your stored water in the liquid state directly to the clean water. So traditionally, atmospheric water harvesting materials based on these desiccant type of materials, for example here, showing the silicon gels, they are highly polar kind of hydroxy group. They're offering these hydrogen bonds and then actually with the water vapor. So zeolite is these 3D network molecules with the silica and also the aluminum with the alkali metals. They often use the aluminum as active sites, but they generally have limited water capacity. Hygroscopic salts that can offer water absorption usually at the lower humidity, but often comes with challenges. They do have the particle aggregation during hydration, so lead to quickly decayed performance for water harvesting. And overall, the key challenge here is for desorption steps. The high energy demand is still needed for water release. So we demonstrate to the field that hydrogel is very unique. Right? They have a very, very functional chemistry that can tune the water-polymer interactions. So they can potentially address these with the thermoresponsive behavior, changing from water-like, so-called hydrophilic state, to the water-dislike, hydrophobic state, without these very big energy penalty you need to pay. And also, hydrogel is highly swellable network, so they can offer these high water capacity. So they do have these two major advantages. So back in the time of around 2017, 2018, as we work on the gels for solar evaporation, we also developed another class of the gel. We call it super moisture absorbent gel. So this gel also contains two key ingredients. One is hygroscopic polymer based on polypyrrole chloride. The other is hydrophilicity switchable polymer that can switch from water-like to water-dislike. And most important, as I mentioned in the last slide, right? So the high barrier that you need to go over for conventional absorbents. Right now, you can have very energy-efficient water release. So as you can see from this slide, there's a video showing water that actually can come out very quickly within these bulk gels with a simple sunlight. And this slide highlights two key advantages, as I mentioned, for SMAC gel base. The first step, you have these highly hydrated states that you have sweatable network, so it really functions as water sponges to absorb the water. And most importantly, they can offer this express mode of water release, so without paying these large energy barriers. So our solar-powered gel-based AWH devices already can produce water yield around 20 to 40 liters per kilograms at various RH. But our first generation has a limitation. They don't work well at low humidity. So in recent years, we already developed a better version, so low-cost gel film made of biomass materials. So they can actually pull the water even from the extreme dried airs. And overall sorbent material cost is only about $2 per kilogram. So in this design, we use renewable cellulose and a common kitchen ingredient called conjugate gum, so they can offer these open structures that to control the loading of inorganic salt to work at the lower humidities, but also with these thermoresponsive properties from these cellulose, they can actually offer very highly efficient water release steps. So what we demonstrate here is at a different relative humidity. For example, in a very dry desert area, so conventional sorbent, they can only produce about 3 liters of water. So this will be from conventional sorbents, 3 liters. If you use our gels, so they can get is at relatively about 20 to 30, they will get all 10 to 11 liters of water. If we use Berlin as an example, around average yearly humidity around 60 to 70%, you can produce how much is over 20 liters of the water, right? So you really need to have a strong man to carry how much water you can produce per kilogram of these active gel materials. Thank you. So material innovation on atmospheric water harvesting can really go beyond. So we demonstrated recently, we can create this concept called self-watering soil that integrates SMAC gels coated with very dry sands that you don't think it's possible to grow crops. Right now, you can turn them to mimic what nature can do. Right? At night, they absorb the water slowly, and at daytime, sunlight comes in, they slowly release water. And in this past summer, we demonstrate a smart soil 2.0. So we incorporate both self-watering effect as well as slow fertilizer nutrient release. So this is addressing another kind of challenges for conventional agriculture. Oftentimes, this over-fertilizing will cause land degradation. So this design potentially can mimic all the nature process, sorption at night, slow release of water and the nutrient at daytime. So this is actually can be helpful design for modern sustainable agriculture. So looking beyond, so to ultimately make breaking the wall of energy water accessibility, it's essential we're all working together, as well as we need to working with many next generation, many young minds, inspiring them as a next generation scientists, engineers, entrepreneurs, to translate scientific discovery to impactful technology to address grand challenges. Thank you.